There are so many deep patterns that are shared by so many organisms, and by, as you say, even the molecules have the same collective action that's going on, right? Like that there's this, part of all that is, and that really all we are these patterns, and we share them with these organisms. We are not separate from them. We actually are filled with exactly the same patterns, deep patterns. And that commonality is spiritual to me.
Welcome to the Garrison Institute presents The Common Good. I'm Jonathan F.P. and in this episode, I'm honored to be speaking with Janine Benyus. Janine is a renowned biologist, author, and co-founder of the Biomimicry Institute. Her groundbreaking work introduced biomimicry as a transformative discipline that studies nature's models to inspire sustainable design and innovation. Through her books, especially Biomimicry, Innovation Inspired by Nature, and Global Advocacy, Benyus has shaped how businesses, scientists, and communities approach design, moving from extraction to regeneration and from competition to collaboration. Her vision merges the wisdom of natural systems with modern science, encouraging human flourishing in harmony with the planet and all its creatures. Benyus's work highlights how a deeper connection to the living world can catalyze spiritual and ethical action for the common good. Welcome, Janine.
Hi, Jonathan. Thank you. It's good to be here.
It is wonderful to have you and to continue our conversation.
Yeah.
So I want to begin at the beginning, and I'd love to hear about your growing up and your insatiable desire to be in nature as you're growing up.
I was fortunate to have, be a free-range child, as they call them now. And even though I was living in suburbia in New Jersey, I had this ravine behind my house. And then I had this wonderful meadow beyond that. And I spent literally every waking hour that I wasn't in school out there. My mom used to ring a bell at the end of the day to get me back in, and I'd have to travel quite a ways to get back. And then my father would take us out canoeing or sailing or hiking every weekend. So for me, New Jersey was full of all these micro wildernesses. But I got to really know the organisms because my play consisted of checking on each and every one of them. Each day I'd run down, I knew who was spinning a cocoon and who was nesting and how the birds were going. And I literally would visit them as if you would be visiting neighbors in a community. And, then I started to be a little scientist, and I'd start to, when I got home, I'd run downstairs and I had microscopes and I'd write out my notes from what I had observed that day. So it was a very intimate relationship with the natural world. Yeah, with the rest of the natural world.
And then you went off to college. Oh, but you had a story about that. You had a story about, I think, disruption.
Well, yeah. And I think this is unfortunately a common one that often lights a fire in people to try to do something about helping to heal the planet. I had the ravine, and then the field was this old New England field. I called it Sir Morton Romp Field. I had an English house name for it. And one day I saw these flags in it sitting on little wires. And I was reading Sherlock Holmes at the time. I saw footprints that I had never seen, so I did plaster of Paris. I got the prints, brought it all back. I've got all these cigarette butts in a jar, and my mother thought I was smoking. I brought it back to my basement and said, well, what is this mystery? What's happening here? And if I had flown over it, I would have seen it was the layout of the phase 2 of our subdivision. So I literally for a summer just sat in the bushes and watched bulldozers, roll away everything, just roll it up with animals, flying towards me. and all of us watching from the bushes, and then put up, cul-de-sacs and dead worms, as Amory Lovins calls them, dead worm design of cul-de-sacs and asphalt and turf. And I thought to myself, if the people who are on these bulldozers knew what I knew about this community, they would do it differently. That was my theory back then. And then at that moment, I sort of vowed to those animals that were flying by me that I would tell their stories. And that's why I became a science writer, biology writer. I wanted to tell the story of life.
And you've actually done an amazing job of that. Okay, so how did you come up with even the word biomimicry and the idea? Because you were the first. I mean, you were very, very early in that.
Yeah, I had written 5 other books, natural history books, and a lot of them were about how well organisms are adapted to their habitats. There was a series, a US-wide series about wildlife habitats that were organized by the habitat. So you walk into a cattail marsh, and this is what you'll see because this is who's adapted to living there. So this idea of adaptation to place became deeply embedded in me until I realized, oh, those are technologies. And we are not very well adapted to our places right now, the way we're living on Earth right now in Western industrial culture. And then I just assumed that people who invented things would be looking to the natural world, like solar cell manufacturers would be studying leaves. Turns out that's not true. And so I started searching for it in the stacks while I was writing another book. And every time I'd find an article, oh, here is, at ASU, there's these scientists who are studying leaves to come up with thin film solar cells that are non-toxic. And I'd Xerox, that's how long ago it was, started in 1990. I'd Xerox that paper. And then I got a folder and I had to name it. And I went to the Oxford Dictionary and I looked up bio in Greek means life. Mimesis is to imitate. And I thought, that's a mouthful. So I wrote biomimicry on the folder, literally. And then it became a file drawer. And one day I walked by and there were 4 drawers. And I said, this is a field that has no name. And it should, because it's happening. But it was just in you had to be a nerd like me to find these papers at that time.
What's interesting is you described organisms adapting to their environment, but it's actually a multi-way relationship. And so the environment also adapts to the organisms because the organisms have influence, but it's a multi-way because it's not just a one-way organism environment. They're all...
And their environment is more than just the temperature and the rainfall. It's all the other organisms, and they're all shaping each other.
Right. And the nutrient flow between them and
That's
the entropy they're creating and all that stuff. So actually, I have a question that's going to come out of that. But first, let's just define biomimicry and give some examples a little bit more for our audience. So what are some things that have been designed in biomimicking ways?
I have a vision right now in my head because I just got back from Sitka, Alaska, where our 2-year master's students are having a 1-week immersion. And we had such whale watching. It was unbelievable. Even the guide said they'd never seen anything, the abundance, and that just fills you with joy. There were so many whales, you had to just keep spinning your head, to see all the blows. And then all of a sudden, this one whale just starts breaching and breaching. And so I can see her flippers. It's a humpback whale. So there are wind turbines, believe it or not, that are based on what are called these scalloped edges along the leading edge of a humpback whale's fin. Now, what happens is the humpback whale, they do this bubble feeding, where they go down, way down deep together. And as they come up, they spiral and they blow bubbles. And they create this curtain of bubbles that trap the krill. And then they all go down, 4 or 5 of them, and with their mouths open through that cylinder, and they get all this krill with their baleen. Anyway, they have to be super hydrodynamic. So the scalloped edges allow them to play and reduce drag dramatically. So if you were to put this, and they're putting this on wind turbines, on fans. I've seen them retrofitting airplane wings. If you put that shape, which plays with drag in a certain way, on an airplane wing, it would reduce the drag by 32%.
Wow.
So these sorts of beautiful things are right in we're surrounded by this genius. We're surrounded by these solutions. There's another one I love that is it's a new company. Our institute does an accelerator. And so we get about 400 biomimetic companies coming to us every year. So this young man from India came over to the States and studied plant chemistry. And he realized that plants talk to each other. Now we know through the mycorrhizal web, there's a fungal intermediary in the wood wide web. And we also know that they put out volatile organic compounds, chemicals, into the air. So when one gets, say, an insect eats a leaf, that plant will respond by releasing these compounds, warning the other plants around it to beef up their defenses against that kind of insect, to not be so palatable to the insect. And the parent plants do it to their fruit. So he went back to India. He realized India is the second largest fruit and vegetable producer in the world. And he realized that only 40% of those fruits and vegetables are getting from the farm to the village because they're on unrefrigerated railroad cars. So what he did was he mimicked, and you also realize that fruits and vegetables are alive for a while after they're picked. A lot of people don't know that. So they're able to respond. But they're away from their parent plant and they're no longer getting the chemicals that say beef up. And all rot is microbes taking over, right? And so he puts in these sachets of these chemicals, biodegradable chemicals, that basically tell the fruits and vegetables to beef up their defenses. And now it's like 50 to 70% longer they're able to live without getting tossed, basically, when the train comes to town. And that's a huge thing because food waste is such a big contributor to climate change. And these farmers are now getting paid for their yields. That kind of thing. There's so many, Jonathan, and also on the systems level, whole cities.
So that's fantastic. I actually want to talk more about the systems level because what's interesting is, so I'm going to take these in levels. So the story of the making the windmills or airplane wings, and I've also heard about biomimicry boat propellers. Yeah. Those are taking lessons from nature and applying them to fixed objects and designing the objects to be more efficient. Now what you've described with the volatile chemicals is something more dynamic.
Yeah, it's a process.
It's actually looking at not just the design of nature, but the processes of nature. And by the way, my understanding is plants can put out dozens and dozens of different chemicals, like they can signal different insects. It's a real language. It's not just one blunt instrument, but you're now taking that language, and that language is stimulating a systemic response, an autoimmune response, versus just a blunt fixed object. Okay, now you said you're going to go up another level, a systems level. So I'd love to hear that.
Yeah, so the first was form, the second was process, you're right. And then at a systems level, we have a consultancy that we work with clients who usually we have done product design for years and process design for years and years. And finally, we started to work with architects, people in your profession, and urban planners and landscape architects. And they said, well, how would a city mimic an ecosystem? Because at the end of the day, that's what we really want to do. We want to fit in here, right? And you fit into these communities. I've watched lots of organisms when I was young learn to naturalize and learn to fit in. You do that by benefiting the other organisms that are there. Mm-hmm. You become a beneficial species if you want to become a welcome species. Mm. Yeah, it's a difference between that and an invasive species. A naturalized species contributes. So that was one of the things. If we were going to come into a watershed and build something, whether it be a building in its site or a district or a city, you would want that city not to look like the forest next door, the wildland next door, not necessarily look like it, but function like it, perform like it, give back like it. And that's one of the biggest things that ecosystems do. They become healthy enough to be abundant to actually give benefits beyond their borders. So what we wound up doing was we found a big ecological modeling company that had worked with the Nature Conservancy to develop a big model that allows us to go in and measure. We go to the closest intact ecosystem. It could be a park near you or whatever. That's pretty much healthy. We go in there and we say, what are you doing? Like, how much water are you storing? How much carbon are you storing? How much cooling are you doing? What kind of habitat support do you provide? How about soil erosion? How about, do you abate noise? Are you like quieting the place? And we look at all those functions that the forest is doing and we actually measure them. Yeah, I'm storing this much water, I'm storing this much carbon. And then we go to the building site and we say, you're building and it's landscaping. Here are the new key performance indicators you need to meet. They're called ecological performance indicators. So that you get, because the performance, we also measure the current performance. And Jonathan, sometimes it's, it's not quite negative, but it sure is the null set. It's like, no, this has been completely bladed and there are no ecosystem services created.
By the way, I'm sure it's negative.
It's really, I've been there a lot, and so have you. Anyway, that's our current performance, and we measure that too. And then we say, here's the ecological performance, and that's this emerald standard, we call it. And we design into that gap. And we say, okay, how would you design if you want cooling? How many trees do you put up? Green roofs, but also awnings. And there's other ways the building might shade, right? So it's this whole, or water storage. I would never think of putting just a sidewalk down now. That's not permeable, and that does not have places for moss to be growing between the cracks. And because I now say that sidewalk should not just hold me up, it should contribute, it should store water. So anyway, we do these designs that are quite, if you try to look at all 21 ecosystem services, I call them ecological gifts. If you try to meet those, your design really changes. And suddenly you're not designing just for yourself. You want like organisms to come and breed and live on your site. The celebration metrics are when, salamanders come back to the little pond you used to have a little waterfall in, right? And now it's full of plants and birds and people are wildlife watching there. And over the years, you can actually measure and celebrate what you're giving back. We call it generous design.
And in fact, that is what makes nature so resilient. I mean, nature's sustainability, its resilience, the fecundity comes from having so many elements that are continuously giving to each other. It's this amazing act of co-creation. And you gave this a beautiful name, the phrase that nature is creating the conditions conducive to life. And therefore, we should really be creating the conditions conducive to life. And I think along with that means we should be recognizing when we're creating conditions that are not conducive to life.
That's right.
So how did it just pop into your mind?
So yeah, it's life creates conditions conducive to life, which is, that beautiful snake eating its tail kind of a thing. It was in the book. But I remember writing it and going, yeah, that's it. It was like something that I had been trying to understand for a really, really long time, ever since I was little, when I would watch year after year. The systems, those ecosystems always got more fecund. They always got more fertile every year. Like life bounces forward. Even if there was a wind gap or a small fire, I'd watch it heal and get more resilient, more fertile, that bouncing forward that it does. And I would think about life enhances places. And then I just started to ask how does it keep getting better every year? And it's because one of the things that natural selection says, yes, please, more of this, is the propensity to create conditions conducive to life. We would often think, well, of course, organisms want to make it better for their offspring. But when you think about it, success in the natural world means your genetic material is still in that population, in that pool, 10,000 generations.
But this whole idea that natural selection or that evolutionary processes are all about producing things for your offspring is a 19th century idea that reflected to me in 19th century colonial. It's like, I'm going to do it for my people view. And actually, that is a mental construct. And I think what we've really learned from nature is that natural systems don't only care about themselves. We see that, for example, when trees share their carbohydrates, they may have a preference for their children, but they share with their communities. And that many, many organisms actually have an instinct, if you can call it that, to share with others. And so I think the offspring preference is a cognitive bias that we've imposed on nature.
It is true that life wants to continue life, right? That is a drive. That continuity of life is a drive that is larger. It's an emergent property. But the only way you can take care of offspring 10,000 years from now is to take care of the place that's going to take care of all offspring 10,000 years from now. That's where it changes. It's really not about the offspring in your generation. Unless you take care of the place that will take care of all offspring, it doesn't matter about your offspring. Do you see what I'm saying? What life is really caring for is to create the conditions conducive to all life. Because the quote unquote habitat is not an abiotic thing. It's a whole community of life. In fact, I love the idea of this word called conbiota. There's abiotic and biotic, right? The non-living and the living. But really, when you start to look at this planet, it's a completely living planet that was co-evolved with life. So conbiota speaks to that it's both and. So that idea that you're worried about your offspring, like we're worried about our offspring. Life is worried that the place that all life will be in, because all offspring depend on other life forms, that place is taken care of. And that shift, foreground, background shift, is a huge one. It's a relieving one, actually, because it allows you to focus on what's most important, which are the conditions conducive to all life, and start to ask yourself, what are those conditions?
And there have been many, many societies in the past, and many indigenous societies still alive today, in which that's a fundamental understanding.
Yep.
It is not a fundamental understanding in our current modern world, but it needs to be. And I actually propose that this view that life creates the conditions conducive to life, and that is our responsibility. That is our moral response. It is, by the way, it is the survival responsibility. It's actually a selfish responsibility in a way. But if we're looking for a universal ethical guide, that is the universal ethical guide. If every action we undertook, we asked, is this creating or reducing the conditions conducive to life? I think we would solve a whole lot of problems in the world today.
I completely agree with you. I completely agree with you. I think it's the central design brief. And I do think that there was a time, and many people still feel this, that they do have a moral responsibility as a species on this planet to contribute, right? To be one of many, the large 30 to 100 million species. We once saw ourselves as very much a part of those, not above those. And that came with responsibility. And the responsibility was this. I think that was a design brief, but it was also, as you say, a filter on what to do and what not to do. Like how to judge the rightness, like Aldo Leopold said, how do you judge the rightness of anything you do? Will it benefit the biota? Will it make it more beautiful?
Right.
Right. That it's a simple thing. I mean, I've spent my life now, when I work with these companies, it is not enough to mimic the tubercles on the humpback whale if you're going to use toxic chemistries and you're going to make it in sweatshops and you're going to ship it across the world. So we've tried to answer that question. How does life create conditions conducive to life? And we use something called life's principles as a scoping mechanism before you even start to make anything. And it's kind of nature's eco checklist. It's what all organisms have in common. And, it has to do with doing chemistry in life-friendly ways. And it has to do with cultivating cooperative relationships. And, does it self-renew? Does it heal itself? What? Why should my fan have to heal itself? And now we've added, like, does your fan pollinate? We've added ecosystem benefits to try to get people to think like, why would it need to pollinate? Well, you've got it it's an industrial fan up there and you've got open windows. Does it allow pollen to flow through well? Why should I do that? Why should my fan do that? See, but every artifact, every natural artifact has to meet life's principles.
Right. Do more. Right. So I just, for the audience, want to just to delve into one example. So when you talk about, for example, non-toxic chemistry, so we currently produce ceramics under high pressure and enormously high temperatures, which we achieve by burning fossil fuels. And oysters can create amazing ceramics using just all naturally available materials at ocean temperature under the water.
That's right.
They don't need to burn anything.
That's right.
So that's just an example of
everything in the ocean. There's a couple of things that are kind of blowaways. Everything in the ocean is living on fresh water. So they're filtering salt water. So they're a desalination plant.
Oh, really? I didn't know that.
Yeah. And mangroves that have their roots in the water, they're living in fresh water. They have to desalinate. So that's like, wow. And also that everything, all the coral reefs and anything that's hard shells or whatever is made from dissolved CO2. So we're sitting there going, wow, we have a lot of CO2. What are we going to do? All this carbon dioxide. And these organisms are quietly in ambient seawater conditions around their own bodies without a kiln making these ceramics, as you say, like abalone, the inside of abalone shell, that mother of pearl, is twice as tough as our high-tech ceramics that are in jet engines. So it's not that they're weak. It's that they're manufactured differently because they have to manufacture in or near their own body.
So this is really interesting. So I'm going to ask a question. I don't know if this works or not, but so leaves have this incredible capacity. They take hydrogen and oxygen from the H2O, from the water from the earth, and they take carbon dioxide from the air, and a couple photons of electricity, and they rearrange the molecules, the electrons, and they create carbohydrates that are the sugars that power their growth and the growth of others. So is that a similar chemical process that's happening underwater, this kind of extracting hydrogen, oxygen, carbon, maybe potassium or something, or phosphorus, and kind of reorganizing them?
Yeah, it's chemistry. There are 6 biosynthetic pathways or chemical recipes. Think about cooking in the kitchen. There are 6 pathways that we know of that take carbon dioxide and turn it into chemistry. Life doesn't really, even a leaf doesn't turn it into electrons to put in a wire.
Right.
It's stored instantly in sugars, as you said. So yeah, there's 6 different ways. And it's talk about the playbook for, drawing down the carbon that's currently in our atmosphere, the legacy carbon. There's they're twin sisters. They have a company called Ruby Laboratories, and they're doing a series of chemistries to take CO2 and turn it into fibers. So, there's lots of people working on biodegradable fibers and working on this. But that's just and people do look at the carbon dioxide, one biosynthetic pathway, but there's lots of them. Yeah.
Okay. So now you're writing another book.
Yeah.
And the book is organized around a series of organizational ideas. So let's walk through the different chapters and the big ideas that are in each one of those.
Well, the book is a biology book. And it's for people who, it's to increase our biological literacy about the world so that we might emulate it. And so I tried to look at realms where, if economists could learn about something about the natural world, what might they be interested in? And so that chapter is how does nature grow and right size and scale? Very important concepts, right? In a pro-growth economy that we have now.
So, but by the way, nature knows how to stabilize. So when we go back to your example of after a forest fire or an earthquake or something, and nature's incredibly fecund and it's growing like crazy, and it's going through, well, it has plants that'll stabilize the soil, and then smaller trees that are growing. It has a whole succession system, and it grows in complexity. But then it reaches, what we used to call a climax forest. It's the wrong name, but it reaches a level of maturity where it has more or less the same amount of energy flow, water flow, material flow in and out of it. Although trees are always being born and dying, and the overall system doesn't just continue to keep growing. We don't get 1,000 feet tall trees.
Yeah.
So nature's growth does, I don't want to say I want your words on this. It's not that it self-limits, but it reaches a balance, and then it focuses more on the balance than on the increase in size, I guess is what I'm saying.
That's right. We would call it, it qualitatively develops, right? Life's always integrating development and growth. So for instance, an embryo grows for a while, and then it makes sure that it develops all the nerves and blood vessels that are needed to connect each cell. So there's like these phases of growing and then developing, and then growing and developing. And one of the things that you see, one of the growth imperatives is that, when I look at a tree, I see it as a distribution network, network of exchange, because I see it as full of, these xylem and phloem, these tubes that are delivering water from the roots, and that are delivering, and now are connected to the mycorrhizal fungi. And then, the sugars that you described are being distributed throughout the tree and throughout the forest. So it's a distribution network. And these systems grow, they don't grow beyond the point that they can deliver nutrients to every cell. And I don't mean every leaf, I mean every cell in that leaf. So that's the qualitative development. Can I get nutrients to every cell? And so a lot of the right sizing that you see is about, that's the right size for a distribution network in this place and with this species. It's interesting that we, regenerative finance folks are beginning to look at some of the energy network science that's been done on flow structures in ecosystems, for instance, or in our bodies. This idea that, for instance, in your own body, it's very important that nutrients get to every cell, or else you have necrosis. But we have been in economic times where we've, for instance, started to shut down local banks and only have regional banks or national banks. And life has all three levels, by the way. They don't just have local banks. They don't just have small distributors to individual cells. They also have, arteries, larger flow networks that are more efficient in certain ways, right? And then they have the largest ones. So they have small, medium, and large distribution vehicles, if you will. You can think about it as large roads or smaller roads or tiny roads, right? That concept of a hierarchy of those different ways to get stuff around is really important. So when we drop local banks, we get necrosis, economic necrosis in neighborhoods that are redlined.
Right.
Right? Like that's how you translate biological ideas into social innovation, is by thinking stuff like that.
That's amazing, because what I also get out of that is, if nature says that we're going to grow to the level, but the prime goal is not the growth, the prime goal is the distributing nutrients, sufficient nutrients to every cell.
Yeah.
So if we organize our economy or society about that, that would mean there'd be no poverty. It'd mean that everybody would be nutritiously fed and housed. And you would say that I'm only going to grow if it enhances our capacity to do that. And any growth that stresses our capacity to do that or limits our capacity to do that, we're not going to do, because it, as you said, adds necrosis to the system. And we see, so equal distribution in a way under that view, to me, currently has a human moral view, but now it's taking on a life principle view.
Mm-hmm. Yeah. I mean, that's it. You have to be very careful when you apply nature's wisdom to social innovation, that you're not doing what they did in the eugenics movement, which was misreading Darwin and misreading natural selection to be survival of the fittest, when he actually said and meant, survival of the fit. So we've been down that road before, and I just want to put that caveat in. But if you choose the right, you don't want like lions as your model or bees. We're not lions, we're not bees. But when you look at the ecosystem level and you look at deep patterns that you see everywhere about, for instance, distribution, whether it's in your blood vessels or leaves or trees, you also begin to realize that the distribution networks, the physical ones, actually have something very much in common. Like your bronchial passages and the roots of a tree have, if you look at it just mathematically, they both describe the same branching mathematics.
Right.
And then they asked why? Why are they mathematically so similar?
That's what's most efficient.
Because it's the way to get things to each cell. So that's when you can then say, this is an important pattern in the natural world.
Right. Okay. So you described an economic one. Keep going. Name it. Let's walk through another chapter.
So then some of the other chapters are, how does nature heal from trauma? Which is one I think everybody says that, Jonathan. Whenever I say that chapter, everybody's like, wow, yeah. Like, I think we're like in need of some of that wisdom. And it is amazing. And it's, you were starting to describe one of the things that life does is this continual, let's call the adaptive cycle. You were talking about a forest that gets to a point where it's very tied together and very closely tight networked. And yet it gets to a point where it's then vulnerable to the next phase of release that happens with a forest fire or whatever. And I get to watch that in real time because I live in the Bitterroot Valley. I live surrounded by wilderness. So I get to see a lot of wildfires. And I get to walk through those places as they heal. And what happens after that release of all of those ashes, and I'm drawing something in if you can imagine, the adaptive cycle, which is taken from ecological research, is a infinity sign. So now we're up the for loop of that infinity sign, or that 8 on its side. We're at the top of it now where the forest literally releases all of its nutrients. And then it curls around and it starts what's called the reorganization cycle or the healing cycle. And that reorganization cycle is where the forest knits itself back together. But that's also where it has a chance to do things differently. Remember, I was talking about bouncing forward. So it can knit itself together with the seeds that are in the bank, but other organisms will come in. There's new ways that things can come together. So as it goes through that reorg loop, which is the fastest part of the cycle, it then gets to a point where, the seedlings are up, the soil's all, held by the root systems. And then next thing you know, it's on its way to grow for hundreds of years from seedling to forest again. And you can really look at that and try to imagine where we are in that cycle.
So I look at the disruption of globalization that is happening right now. And as a consequence, by the way, not just the globalization the disruption is happening right now, but the multi-generation of it. And there are places in Appalachia and places, I'm sure, in Montana, and there are places here in the mid-Hudson River Valley, which have been disconnected from the globalization loop. And in many ways, economically, we would have said they're left behind, but actually what I think is they're the places with the most opportunity because they're not already bound into a constraining system of a global finance or a national finance system and a national politics. They actually have the most potential. As you said, that's a reorganizing loop to reorganize themselves, find their own natural fitness to their bioregion, and then reemerge.
Yeah. That's right. That's right. That you had talked of them as islands of coherence when we were speaking before. And there's another biological analog to that, which is the way a forest starts its journey back to health is very different from when, we take a devastated field, say in the rainforest, and we're going to restore it. So we put trees in rows, like corn,
Right.
which is like, that never happens. So what actually happens
Right.
If you watch over long periods of time something come back to life, it starts with islands. Okay, so what those islands are that are in the open, imagine this open field, and then a bird comes and it lands on, one piece of grass that's left, poops out a seed, and then that seed grows into a tree or a little seedling. But then what happens is it creates a protected area behind it. If it's, it creates a windward and a leeward. So anytime you start something, like if you even start an organization, I always tell people just start. Just start something, because then you create conditions conducive to life behind you. Literally, that's what happens. So all around, once one gets started, I'm in the sun, it's pretty hot, but there's shade behind me. That makes it available for other organisms to get going. And then more birds come, they bring different kinds of seeds. So suddenly you have this mixed species group. And it's in a little small, roundish island. But if you look across the field, there's many of these. And what happens in restoration is that they congeal. Natural regeneration is they congeal. And that, if you compare that, and I've stood in forests, and we do it as a management practice, it's now called applied nucleation, where we actually you just go out and put, stakes in a field and invite birds in. You do an invitation, and then you start to build this to start that regeneration the way the natural world does. I've been there, and it's much more biodiverse than, say, a plantation where you're every few inches, which is the engineering way to do it. It's not a biomimetic way. The biomimetic way is what you're talking about. And Christopher Alexander talked about, in The Nature of Water, talked about these centers and holes in a city, right? And just make sure you get the centers right. Make sure you've got the cafe on the corner with the bench and the tree. That's a center. And that invites people in, right? Yeah.
So also, we think there's a lot of talk now about individual trauma and the healing of individual trauma. And one of the points that Dan Siegel has been making is you cannot heal your trauma individually. By the way, part of it is connecting parts within yourself. But the healing of trauma is a we activity, not a me activity. It's actually psychodynamically, sociologically, it is you heal as a collective, you heal in relation to others. It's very hard to just heal on your own. And you heal much faster when you're healing collectively and you're part of a healthy community. So that's just another parallel.
It's so true. And, Jack Saul saw that too, right? In communities that were devastated after hurricanes or whatever, how people heal collectively. And that's this idea. There's another idea that's more than even a hypothesis right now. It's been proven so many times, and it's called the stress gradient hypothesis, which is counterintuitive to the way we think. But it's shown that as conditions on the ground get harsher, organisms they get into positive groups that help each other, facilitative groups, more than they do in easy places. So when you go up to the top of a alpine, where a lot of this work was done up in Chile, you see these beautiful cushion plants, yarrow plants, and they're a kind of a mossy looking kind of plant, and tucked in there's all kinds of other plants, flowering plants that grow, and they protect each other from the wind and the harsh conditions. The propensity to collectively get together to handle those conditions goes up in stressful times. So that doesn't surprise me that after a hurricane, we're helping each other.
So we need a little stress. We need not too much. Okay. So what's another one of your chapters?
There's a chapter about how does life self-organize for collective action. I guess, that's one that we're talking about now. And how does that, in this book is called The Universals. They're nature's universals. Right. But I'm looking at patterns, and I don't just look at patterns at one scale or like, what do primates do? I'm looking literally from the molecular to the biospheric to look at those sorts of deeper patterns. So collective action can happen on the level of cells, and it's so beautiful how cells collectively work together to do things.
Well, first of all, a cell is a collection, just of the mitochondria and the cell. I mean, a cell already is a joint
Yeah, tell
venture.
about that. Tell about the endosymbiosis.
Well, go ahead, you do it.
Well, yeah. I mean, every eukaryotic cell was two separate beings, one bacterium that engulfed another, ingested it, but didn't digest it. And then that border within had a different skill set, which was it could respire, it could break down food with oxygen. That became our mitochondria in every animal cell. And then every plant cell, it was a chlorophyll. It was a photosynthetic bacteria that was ingested, but not digested.
But for example, the mitochondria, they have actually different DNA than our main cells. So they're literally a different organism. Every one of our cells is actually this joint venture between a mitochondria that's providing energy and it has its own maternal kind of genetic path
DNA.
From the rest of the cells. So
right.
I actually want to go back to you use this word self-organizing.
Yeah.
And yet we think of self as meaning individual.
Yeah.
So I know what you mean by self-organizing, meaning not externally motivated, but kind of internally motivated, but it's really collective organizing.
It is. That's right. It is, because what you're talking about is a collection of agents that are, the system is the self.
Right. And we even it's so interesting. This is a problem with our Western modern language. When you mentioned a tree, I have a Hopi friend who says, we see trees as a verb, you see them as a noun, and you described it as a process. And so even, we use this thing of agents, which represent an individual, but in fact, what we're learning is that nothing, every organism has microorganisms within it that are affecting it. And we have vertical gene flow and horizontal gene flow, and it's like all so interconnected.
Totally.
And whenever we disconnect it, it degrades its health.
Yeah.
And when we reconnect it, it grows its health. And so we almost need a modern language that eliminates the atom in a way and sees the flow.
Exactly. I have a really hard time like self-healing.
Yeah.
It doesn't heal itself. It is always collective. Right. So it is in our language. Yeah. I mean, our language is really interesting to me. I've thought a lot about why we in Western industrial culture are just coming to biomimicry now. Coming to look to other organisms who might have wisdom, and it's in our language. We talk about the lower kingdoms, higher primates. It's right there. How othering our whole colonial journey has been, how othering and how human supremacy has I have gone to conferences where scientists, knowing I was in the audience, their first slide is biomimicry with a universal / sign through it. They're engineers.
Whoa.
Yeah.
You shouldn't even go to those conferences.
There's a particular engineer who loves doing this. And what he says is basically where we don't literally, they use this word slavishly or slavishly imitate the natural world. We get some ideas, but then we go beyond nature, beyond what nature can do. And I'm like, really? So I have these conversations because I go up afterwards and I'm like, let's compare something. Let's compare a solar cell to a leaf, right? Well, it's much more efficient. Yeah, but what happens at the end of its useful life? A leaf can create more leaves or mushrooms or, right? That whole conversation about where you start bragging about something, once you put a lot of what we've done into a system in Western industrial culture, and once you put it into a system, it pales, right? It really, really pales. And yet there is this idea that, what could we possibly learn from these organisms? I think that's diminishing. But certainly when we first started this work, it was seen as quite odd that you would traffic with the lower organisms.
So,
yeah.
By the way, there's a writer named James Bridle who has a phrase that everything is equally evolved.
Yeah.
So if you think about it, the Big Bang happened 13.2 or whatever billion years ago. And then every atom, every organism, everything that exists today are all 13.2 billion years old.
Yeah.
They're all equally evolved. None is older than the other. None is more evolved than the other. They've all evolved over that whole long length of time.
Yeah.
And what has grown, what you can say has grown more is the complexity and integration of the system.
Yeah.
So you can rank the systems by, but you can't say that this is a higher species and that's a lower species,
Right.
because they all rely on each other.
That's right. They're not like life doesn't make things. Life makes things disappear into systems, into community.
Yeah. Anyway, I would say to those scientists with the nullify biomimicry, great. Just, why don't you just continue on with no bacteria and microorganisms in your life? Just eliminate, like just purify yourself, get rid of all those and
Exactly.
don't touch anything that was made by microorganisms and bacteria.
Exactly.
And, just live in your higher realm.
Exactly. It's so incredible. Anyway, but it's very few. It's a very small number. Most of the people that are doing biomimicry as a practice, where they're looking to the natural world for answers, for guidance, they're very humble. It humbles you
Right.
to try to do even this, just to come closer to how spectacular these organisms are.
So there's something that's inspirational about it. There's enormous, many lessons, and we only discussed a few of the lessons that you can extract from it. But then there's something spiritual. And you said to me, it's like looking into a stream and seeing the face of God.
Yeah. That's been the journey of writing this book on nature's universals for me. I have the luxury of really having gone through about 29,000 papers and about 280 books to really revisit where we are, both in Western science and indigenous science. And think where biology is coming right now is maybe a point that, the quantum physicists came to, where there are so many deep patterns that are shared by so many organisms. And by, as you say, even the molecules have the same collective action that's going on, right? Like that there's this, part of all that is, and that really all we are these patterns. And we share them with these organisms. We are not separate from them. We actually are filled with exactly the same patterns, deep patterns. And that commonality is spiritual to me. The fact that there's unity in the diversity, I find the diversity beautiful. I find the unity spiritual. Yeah, it's incredible. I mean, just, we talked about growth, and the other way nature grows is through networks. So we only talked about individual growth, but really nature grows through networks, right? It connects to more and more of itself and to other networks, right? And now when we look at those networks in biology, whether it's our brain cells or the gene regulation networks, protein regulation networks, mutualism networks, food webs, all these networks in the natural world, it turns out they've got incredible architecture and structure to them that is similar, whether you're looking at a food web in the Everglades or you're looking at a plant pollinator mutual web in the Alpine Rockies. The way they organize themselves in a network is very, very similar depending on if they're in a mutualistic network, you can look at how it's organized, meaning, what organisms are interacting with which organisms and what processes. They have these things called network motifs, which are the processes that they do, the communication processes. Those are, even though there's so much diversity, we've realized, oh my gosh, here they are. They fall into these categories that are similar to some of our networks as well, our social networks. And so for me, part of what got us into this issue where we don't feel like we feel like we're not part of all that is, we feel like we're superior. Part of that was that we didn't see the commonalities. And so it kind of is a scales from your eyes kind of moment when you see those deep patterns of flow, of network, of cycles that we're a part of. We may be monkey wrenching some of the flows right now. We might want to stand back from that monkey wrenching and join these beautiful cycles. That's my hope.
It's interesting. Part of that, I don't know if it's the motto of the United States, but the phrase e pluribus unum,
Yeah.
which means out of many one.
Yeah. Yeah.
I think they wrote it as a political idea, but it's actually a spiritual idea.
Mm-hmm.
And if it's obviously a biological idea. And it'd be amazing if we could actually live by that.
Yeah.
It would be e pluribus unum to create the conditions conducive to life.
We hold these biological truths to be self-evident.
Ooh, you got it. That should be the subtitle of your book. We hold these biological truths to be self-evident.
Yeah. Yeah. It's just us trying to learn to be good earthlings, really. And that's what every species walks through that learning journey. Every species learns how to be an earthling here.
And by the way, lots of humans have learned that.
Yeah, that's right.
There's a lot of indigenous cultures. It's just we're currently living in this distorted culture.
It's so crazy.
Right. Well, Janine, thank you so much for giving us a pathway forward. Your work is really elucidating and illuminating a holistic way of thinking that actually will help us flourish. So I'm very, very grateful for this conversation, and really, we are very lucky to have you in the world doing this work.
Oh, Jonathan, you as well. I can't wait for your new book and for this rich conversation.
Thank you. And I look forward to seeing you again.
Yeah. Well, Montana awaits.
Thank you to our guest, Janine Benyus. The Common Good is a production of the Garrison Institute and is hosted by me, Jonathan F.P. Rose. We'd love to hear your thoughts about the podcast. Please send us a note at podcasts@garrisoninstitute.org and let us know what you think. If you've enjoyed this episode, please consider leaving a positive review on Apple Podcasts. This show is produced by the Garrison Institute with production and marketing from The Podglomerate. Its theme music was composed by Jonathan F.P. Rose and performed by Jog Blues. We look forward to being with you again soon.